Good morning, ladies and gentlemen. Today we're going to look at expectation. So expectation uses what we learned in discrete probability outcomes and distributions last video. But this time we're looking at what is the average expected outcome. So if we roll a dice 120 times, how many times do we expect to roll a 6? Well, the probability of rolling a 6, so the probability of getting a 6, is equal to 1 in 6. No surprises there. So the number of times we would expect to roll a 6 is 120 times a sixth, or very simply 20 times. Now, that doesn't mean we're guaranteed to get 26s, it just means that on average we would expect to. And this is put in a whole bunch of scary notation. So here, the expected outcome of a distribution is equal to, we can call it the mean of the distribution. And this notation here means for all I equals 1 up to n, so for all possible values of I, which is each one of these here, 1, 2, 3 to n, we take the outcome, which is xi, and multiply it by its corresponding probability, the probability of that outcome, and we add them all together. So it produces one little long line like this. Notation is scary, so let me do it in a more simple example. What is the expected outcome when rolling a dice? Now, we all know what dice looks like, 6 sides, and we know that the probability of getting a 1 is 1 in 6. And we can add that to the probability of getting a 2, 1 in 6, and the probability of getting a 3, which is 1 in 6, and a 4, and a 5, and a 6. What's happening here is this here is the first outcome. That's x1, and that's the probability of the first outcome. And no, it won't always be the same probability, but clearly with a dice it is. This is the second outcome and the second probability. And all the way up until we get to the final outcome and the final probability. And then we just add them each together. And it turns out the expected outcome for a dice is 3.5. Now, note here that when rolling a dice, we can't actually roll a 3.5. And that's why this is often useful to think about as the average outcome or the mean outcome. Because the mean doesn't have to be a member of the data set. So, for example, if you're looking at shoe sizes in the class, the average shoe size of our class could well be 9.3. You can't buy a shoe with size 9.3, but our mean, or the average shoe size, could well land on 9.3. So quite often the expected outcome is not one of the data set, but it's halfway in the middle, or in between. And we'll look at quicker ways to calculate that in our computers later, or calculators later. But the by hand calculation looks like that, and the notation that matches it is that there. So, now we're going to look at, very quickly, the concept of a fair game. In gambling, the expected gain of the player from each game is the expected return or payout of the game, less the costs of them to play it. So in gambling, the expected outcome for a player will always be negative at a casino, because the house expects to win, you expect to lose. A fair game is when the expected gain is 0. So overall, a fair game, e to the x is 0. So for example, if you're rolling the dice up above, and you win $1 per dot, so roll a 1, you get $1, if you roll a 2, you get $2, you roll a 4, you get $4, etc. What is the probability, or what is the price that would make this game fair? So if you paid $3 to play each game, every time you roll you have to pay over $3. On average, you would expect to lose 50 cents per game, because the expected outcome for a dice is $3.50. If you paid $3 a game and the expected outcome was $3.50, you would gain 50 cents each. If you were paying $4 per game, you would lose 50 cents each. The price here to make it a fair game is $3.50, meaning for every time you roll the dice, you pay $3.50. On average, you expect to win $3.50 back. meaning the total outcome for the game to make it fair is 0. So another example would be roulette. For those of you who haven't played roulette, the wheel works like this. There are 18 red numbers, 18 black numbers, and 1 green number. Each number has an equal chance of occurring. If I place a $2 bet on red, if red is spun, I receive my $2 back plus another $2. Otherwise, I lose my bet. Calculate the expected gain from this bet. Alright, so here it helps to draw up a probability table. So there are 3 things that can happen here. Either we can have red rolled, black rolled, or green rolled. Red, black, or green. And the outcome here, for red, the outcome would be plus $2, a gain of $2. For black, there would be a loss of $2. So when you place your bet, if you roll red, overall you're winning 2. If black is rolled, you're going to lose that $2 bet you've placed. Green, you're also losing 2. So these are the outcomes. And the probability of these outcomes is 18 on 37, because 18 of the 37 numbers are red, 18 on 37 are black, and 1 on 37 is green. So the expected outcome of this game, expectation of x, is 2 multiplied by 18 on 37 plus minus 2 multiplied by 18 on 37 plus minus 2 multiplied by 1 on 37. These two are the same but opposite in sign, so we'll cancel each other out. The expectation of x will be minus 2 on 37. And if we chuck that into a calculator and work out what it is as a decimal, it's going to be quite a small number, but that's okay. It'll be minus 2 divided by 37 is about negative 0.54. 0.054. Which means that the expected gain from this bet is a loss of about 5 cents. So every time you play this game, you're going to lose about 5 cents. If we play the same bet 100 times, what would the expected result be? Well, the expected result would just be 100 times that. So 100 times that, you are expected to lose $5.41. Alright. Okay. We'll do more examples on expectation. The important thing to remember is that it doesn't have to be one of the outcomes on the table. So expected value of a dice is 3.5, and that there is a formula for calculating it. Alright, thank you very much.